This is Fatehpur Sikri, the fascinating ghost town built by Akbar, the Mughal ruler. Arjun Bhagat, amateur photographer and art enthusiast, is wandering through this World Heritage Site. He reads up that Akbar built this to honor the saint Salim Chishti, who promised him sons. Even today, devotees flock to this site to pray to the saint. The city was intended to have been the Mughal capital, but because of scarcity of water, was never used and lies in beguiling emptiness since. Arjun finds the architecture stunning, but what really catches his eye are the patterns everywhere. In the jalis, on the floors, on the walls. Each pattern has been made with a range of shapes: interlocking hexagons, triangles, six-pointed stars and pentagons. He wanders through, trying to see and photograph the myriad patterns that surround him. Clearly, a love of geometry has infused this kind of architecture. The shapes come together to form infinitely expanding patterns. His curiosity is sparked. Around the world, these kind of patterns resonate in Islamic art and architecture. Arjun wonders how certain shapes come together to create these magical patterns and how mathematical they are. This episode of the Maths Factor is all about patterns. Well, the mathematical word for them is a tiling or a tessellation. And through our exploration of tilings, we will see how maths is not just about numbers, but as much a study of patterns. We are going to show you how tilings work in Islamic architecture and Indian Rangoli. We will also take a peep into the world of the famous Dutch artist M.C. Escher and the English physicist Roger Penrose. But before we set off on that journey, let's learn a little bit more about tilings. Arjun is back from Fatehpur Sikri. Still fascinated by the patterns he saw, he looks up images of other tilings in other great monuments around the world. Now, what exactly is a tiling? A tiling is filling a flat surface on a single plane with one or more geometric shapes called tiles without gaps or overlaps. It can be extended infinitely. Now Arjun tries to see what shapes fit together better and the mathematics behind that. He tries his hand with circles first. Could he try and tile a surface with just circles? There are gaps, aren't there? Squares work better. It's pretty obvious that they fit together and create a pattern with no gaps. What other single shape works? Triangles and hexagons. See, we can create a pattern with no overlaps and no gaps. In a sense, 6 triangles form a hexagon, so the tiling of triangles and hexagons are similar. How about a pentagon? Well, that doesn't seem to fit together so well. Wondering why? What we just saw, the squares, triangles and hexagons, are called regular tilings. They are formed by repeating a regular polygon. Now in a regular tiling, each vertex must look the same. What do we mean by a vertex? The point where the corners meet, like this. Now here is something else that happens at the vertices of regular tilings. If we add up all the angles, what do we get? Well, in this case, in a square, all of them are right angles. So we get 90 degrees plus 90 degrees plus 90 degrees plus 90 degrees is equal to 360 degrees. Now what happens in a triangle? These are all equilateral triangles, which means each angle is 60 degrees. So at any vertex, there are 6 angles: 60 degrees, plus 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 60 degrees is equal to 360 degrees. The same thing will work in a hexagon. So what happens in the pentagons that do not fit together? To figure that out, we need to work out the internal angles of a pentagon. When we collapse this pentagon, it is evident that the sum of the exterior angles of a hexagon add up to 360 degrees. Which means that each exterior angle is 360 divided by 5, which is equal to 72 degrees. Which means that each interior angle is 180 minus 72, which is equal to 108 degrees. Now what are the sum of the angles at the vertex? 108 degrees plus 108 degrees plus 108 degrees, which is equal to 324 degrees. Now to create a tiling, the sum of the angles at the vertex needs to be 360 degrees, which is why pentagons cannot form tilings. Now back to Arjun, who is still pondering over the tilings he saw. Now all the patterns in Fatehpur Sikri were clearly not regular tilings, were they? What he saw was a combination of simple shapes forming fantastic designs. So what are these called? Some were semi-regular tiling. Arjun tries his hand at creating them. He creates one using triangles and hexagons, and another using squares and triangles. As Arjun works on creating more of these, what we notice is that they are formed by regular polygons where each side and angle are equal. The arrangement of polygons at every vertex point is also identical. Now, curiously enough, there are only 8 semi-regular tiling. There could be other combinations, but these may not extend infinitely. And some people allow curved shapes, not just polygons, so you can have tilings like these. Back on our journey to explore the mathematics behind patterns, we now head to 2 famous sites: the Imam Reza Shrine in Iran and the Shahi Zinde, a mausoleum complex in Samarkand in Uzbekistan. The patterns here and in many other Islamic monuments around the world are not just stunning. They have a level of mathematical sophistication that wasn't formally developed until hundreds of years later. If you think about it, the only mathematical tools that the builders had were a straight edge and a compass. But the patterns in these structures were astonishingly perfect, even over very large areas. This perplexed Peter Jelu, a Harvard graduate student in physics. He figured that there must be some method at work to achieve this kind of perfection. And so he studied the tiling in detail. He found that he could break the patterns into recurrent shapes. Lou suggests that Islamic architects used these shapes, which he calls giri tiles, to map the patterns onto the walls. Let's move to the studio of a young artist, Shams Alam, to learn a little bit more about giri tiles. Very simply, it is a set of 5 tiles of different shapes: a regular decagon, a bow tie hexagon, a regular pentagon, an irregular hexagon, and a rhombus. Now Alam uses these tiles to create a magical pattern. And then he creates yet another. These giri tiles basically work as unit cells and can be used to create a multitude of patterns. All these patterns can be replicated and extended across an entire plane. So what the workmen must have done is use these pattern templates to replicate them, which explains how they tiled large surfaces with such precision and perfection. How about a game of football? And there is a point to this question. If you've ever looked at the patterns on a football, you will realize that it's a bit like a tiling. The only difference is that it is not on a flat surface, but over a sphere. Now, if we stop playing and look at the ball in more detail, what patterns does it have? Hexagons and pentagons. Now, most footballs are composed of 32 panels, 20 white hexagons and 12 black pentagons. Wondering why? Well, on a football, there are exactly 3 faces meeting at each vertex. Now, if that needs to be kept too, then the pattern must consist of 12 pentagons and 20 hexagons. If you lift this requirement, many other designs become possible. I think after all this football, we need some liquid refreshment. So let's head to the local juice stall. Now, when we see the way the fruit are stacked, there is a logic at work that is similar to creating tilings. Now, mathematicians, starting off with Johannes Kepler in the 17th century, have studied the densest packing of spheres. This means the packing that takes the least amount of space. Now, Kepler believed that the densest configuration is the one you observe with oranges, or in this case, mosmi at the fruit market, which seems to be true, but actually has never been mathematically proven. Our young friend Raja decides to run a small experiment to explore the best way to stack spheres. He is going to do this with marbles instead of oranges. For this experiment, he has lined up some marbles, a glass with a lid, a measuring cup, and some water. First, he fills up a glass with these marbles. He does it in a higgledy-piggledy fashion, without bothering to stack them neatly. He then pours water into the glass to measure the total amount of space left between the marbles. He then needs to measure the water and pours it into the measuring cup and makes a note of the level. Raja is now going to repeat the experiment. He takes another glass and fills it up with marbles. This time in an orderly manner. He then repeats the process. He fills this glass up with water. He measured the water in this case. As he notes the level in the measuring glass, he realizes that there is more water this time, which means that the marbles took up less space when stacked in an orderly fashion. What do we learn from this? That there is a science to packing, and that mathematics is part of almost every part of our lives. On a journey through the magic of tilings, we are going to travel to the studios of Mihir Srivastav, who is exploring the work of M.C. Escher, the famous Dutch artist whose imaginative work married the world of art and mathematics. As he reads, Mihir learns that Escher was born in Leeuwarden in the Netherlands in 1898. In 1926, the young Escher visited the legendary palaces at Alhambra in Spain. The palace here was originally built by Muslim Moors in the 14th century. He was fascinated by the rich possibilities latent in the divisions of a plane surface that he found in these Moorish tilings. He studied these artworks deeply. Fascinated by the beauty of the maths of these patterns, he pondered. For me, it remains an open question whether this work pertains to the realm of mathematics or to that of art. He then started working on creating art based on these patterns. The journey was not easy, but he managed to create the most astounding art that spanned architecture, perspective, and impossible spaces. Combining an innate understanding of mathematics and art, Escher created hundreds of tessellated patterns with fish, frogs, birds, crabs, humans, and other beasts. Now Mihir explores some of the techniques that Escher may have tried out. He is then going to try his hand at creating a tiling of his very own. One of the basic principles behind Escher's art is translation. This uses what we call the addition and subtraction method. Let's see how that works. Start with a simple square. We then subtract a portion of it from one side and add it to the corresponding opposite side. Thus, the resultant shape still preserves the ability to tile. We then use this shape over and over again to create a tiling, a bit like Escher must have done to create this work of art at the Liberal Christian Lyceum at The Hague in 1960. The next device that Escher used was reflection. As the name suggests, all this involves is the flipping of a shape. You can flip it left to right or top to bottom. The third device Escher used was rotation, which is basically moving an object in a circular fashion around an immovable central point. The fourth was glide reflection. Here, reflection and translation are used together to create patterns. Having studied all this, Mihir settles down and tries to create his own artwork. He is working with the basic form of a fish. He uses the technique of reflection to replicate the shape over a plane. He then transfers this onto canvas. And voila! We have our own Escher-like tessellation. Closer to home, we can see mathematics in the rangoli that we do during festivals and to decorate our houses. Now Satyavati is trying her hand at a traditional rangoli that follows the same principles as a mathematical tiling. It's quite beautiful to see it unfold, isn't it? Many people believe that these keep bad omens out of the house. The more complicated they are, the better they are at keeping away bad thoughts and spirits. Satyavati is focusing on the pattern. The mathematics is intuitive for her. The pattern she is making has line symmetry, that is, folding or mirror symmetry. It also has rotation, which is turning symmetry. So you can spin them around, and on the way around, they match up with their own starting position at least twice. Now, not all rangoli patterns are tilings. Many have gaps and can't stretch out to infinity. But this one matches the requisites of a classic tiling. Satyavati adds the last finishing touches. And there we have it, our own Rangoli tiling. Before we wind up, I want to talk about Roger Penrose, a professor of mathematics at the University of Oxford, who also started playing with tilings after seeing the world of Escher. Penrose began to work on the problem of whether a set of shapes could be found which would tile a surface but without generating a repeating pattern, also known as quasi-symmetry. Let's see how that works. We explored earlier that pentagons cannot create regular tilings, unlike squares, triangles or hexagons. Now Penrose took the pentagon and created interesting subunits from it. One set which he called the kites and darts. He then used these to create thick and thin diamonds or rhombuses. Now Penrose demonstrated that when these are put together in certain ways, they have the capacity to cover an infinite plane in an uncountable, infinite number of arrangements. So you will get local symmetries, but no specific pattern is repeated. This system is called aperiodic. And if we cease to look at the mathematics, we can still admire the beauty. A bunch of simple shapes, squares, hexagons, triangles, all leading to a world of magic. We've seen a host of tilings in this episode, explored the world of Islamic architecture, and checked out the art of M.C. Escher and the patterns of Roger Penrose. No time for more, but keep watching the Maths Factor for more magic in mathematics.